I'm going to introduce Don Johnson, who's the chair of the next session.
Thank you, Don.
So the point of this session is to talk about the new faculty that are here and what they're working on. They're not all from the department, but we don't care at Rice. We crossed our departmental boundaries with abandon. It doesn't really matter. As Jim McClellan was an early example of that with Dick Tapia. I mean, that's just the way it was. I have a personal note, though, I'd like to talk about how I got here, because it's interesting. So I'm from Texas. Probably didn't notice, you probably noticed now with my accent. But I went to high school in Memphis. I was applying to colleges. I applied to Rice, MIT, and Georgia Tech. Got rejected at Rice. Got accepted to MIT and Georgia Tech, and I decided I might as well freeze out for a while. As an undergraduate, I became interested in perception. I was a double E, of course 6, right? Of course. But I got very interested in perception, particularly the visual system. And after my senior year, I was going on to graduate school there. I needed a summer job, so I applied to a place called Lincoln Lab. The interviewer was Tom Stockham. And Tom was interested at the time in developing a homomorphic model of the visual system. I mean, I knew zip about signal processing, but he and I hit it off, and I got hired. And unfortunately, I didn't get to work with Tom very long because that's the summer he went to Utah. But I still learned a lot, and I got in Ben Gold's group. This was a gold mine. So I met Charlie, I met Ben. This was really great. I went back to Lincoln every other summer, going back to graduate school, working on the auditory system. I'm still a neuroscience guy. And the second summer there, the last summer that you were at Lincoln, I was working with Al. And we were doing some image processing things. And Al was trying to get ready to teach the course. He was going back to MIT, and I had Golden Radar in my hot little hands, and I knew some DSP, only because I had that book. And I had to do the things I was doing with Al. And so Al needed a TA for the course who knew what DSP meant, what's a Z-transform. And so I got he asked me to be a TA, and he says, by the way, I want you to take it for credit at the same time. So I had to work the homework problems before they were handed out to everybody else, and some of them weren't doable. I still have vivid memories of this. And as Al said earlier, I had to take the quiz before it was handed out to everybody else. This was, I guess, your sense of fun. I had a lot of fun doing that. I was still spending my summers at Lincoln and going back to campus working on the auditory system. In 1973, Tom Parks went through Lincoln on his way to Germany, spent a summer at Lincoln Lab, and I was his office mate. And also with Dan Dudgeon, it turns out. And that's really important because Tom was at Rice. And so when I finally got my degree, I stayed at Lincoln for 3 more years, and I finally got froze out. Boston gets a little cold, got tired of shoveling snow. I call up Tom Parks. I say, Tom, is there an opening of the faculty at Rice? He says, no, but stay tuned. And it all worked out. That's how I wound up at Rice. It turns out because of Lincoln and Stockham and working with Al. I mean, it was really a cool thing. I'd never met Burrus before I interviewed, right? I think that was the first time I met Sid. Anyway, new faculty. What happened to you? Did you crash?
Yeah. It was a soccer injury.
Soccer. He's a bike rider. That's why I'm here. Santiago Segura?
Yeah, thank you.
Oh, you're up.
I'm up. Thanks a lot. Thank you, Don.
And I'm going to be ruthless on
That's perfect, yeah. It should be on spot. Yeah, so thanks a lot. My name is Santiago Segarra, an assistant professor here, and it's a real pleasure to be presenting my work in front of this audience. So I work on data science for networks. So what I mean by this is just, it had to happen. What I mean by this is my idea is to combine network science and signal processing to leverage the structure of networks in order to better understand data defined on them. Okay? And this idea of jointly encompassing both network structure and network data is what I call data science for networks. So you can think of it as having these three pillars. So understanding networks there in the top, understanding network data, and then an empirical side of it. And what I do, can be projected into this triangular space. Okay, but let me just draw your attention to the blue part over here, which has to do with understanding network data. And we do that via something that we call graph signal processing. Okay, so what is this? So this is the analysis and processing of graph signals. And graph signals are signals defined on the nodes of a graph. Okay, so you can think of having a transportation network as being your underlying domain, and then you have congestion levels at different intersections as your signal. Or you can think of having a brain network as your domain, and then having cortical activity at different neural regions as your signal. Okay? And then what kind of things do we want to do to these signals? Well, the same things that we do to other signals. Okay? Sampling, reconstruction, deconvolution, filtering, denoising, etc. Okay, but all these tools, when looked via the lens of graph signal processing, have a network science flavor to them. Okay? So for example, can you interpolate a brain signal from local observations? Well, that's like sampling and reconstructions, but on graph signals. Okay? Can you denoise the power profile and energy network? Or can you detect the source of a rumor in a social network? Okay? So one can say that the general philosophy of graph signal processing would be to grab all these tools that were originally conceived to process signals that lie on very regular domains, like times and images, and extend them to the processing of signals that lie on irregular domains, represented by networks. Okay? So one way to go is you first analyze the Fourier analysis. Okay, you can define Fourier transforms in graphs. And once you get there, you can go crazy. Okay, talk about filtering, system ID, and blind deconvolution. You can even go to the statistical signal processing side and talk about graph stationary processes and power spectral estimation, even graph wavelets and other kind of frames. So this is great. And you can even work on top of it and say, okay, instead of using convolutional neural networks that just classify images, which are very regular grids, what if what I have is a molecule, and I want to classify the chemical properties of this molecule? Well, you can do graph convolutions without graph filters in order to apply this new technology to this new type of signals. Okay? And then we apply this to different interdisciplinary applications, some of them in literature, healthcare, or political science. Okay? But let me just use my last 20 seconds to actually say the following. So I really think that graph signal processing is a perfect testament to the perennial nature of signal processing that Jean was referencing before, right? Because we have these new kind of signals, okay? But the framework, the mindset, and the theoretical understanding of the foundations of the signals is what persists over time and will persist in the future as well. Okay? Thank you.
Good afternoon, everyone. My name is Ying Lin. I'm a new faculty member in the department. So this event has made me feel very humble and fortunate to be part of the family. But of course, also some good pressure, because I start to think about what my research will converge to and how I will look like in 20 and 30 years. Going back to my research, my group focused on embedded algorithm. So we developed technique for bringing powerful machine learning system to resource-constrained daily life device. So next, I'm gonna talk about use a few slides to show what I really mean in this title. So I think we all heard about a lot of big news about machine learning. Here I listed 3 examples. The first one is Google's machine learning systems. AlphaGo beat the human champion in the Go game. And the second and the third one is machine learning beat the human in programming and reading tests. I think what makes us excited about all this big news is not just because machine learning now can do better than human. They can now do things we used to think of, for example, programming, reading. We used to think all these things only human can do. So because of the different breakthrough machine learning has made, it's natural that we believe machine learning gonna have a tremendous impact in different aspects of our daily life. For example, transportation, healthcare, and science, I would say the list is really endless. And we all know behind this excitement of machine learning, there are two driving forces. One is the available of big data. The second one is much more powerful computer. This means when we run the algorithm, it involves a large amount of data movement and also a lot of computation costs. Both of these lead to large energy costs. So in the next example, I'm going to show what I really mean large energy costs. So going back to the first example I mentioned earlier, Google's AlphaGo system, which beat the human champion in the Go game. So in this game, we are all amazed by the performance, AlphaGo. But if we look at the underlying cost, here I do a side-by-side comparison. So AlphaGo needs over 1,000 CPU and almost 200 GPU. And in terms of power consumption, commonly cited human brain power consumption is 20 watts. But AlphaGo needs 1 megawatt. And there are also huge gaps in terms of cost. So what I want to mention in this example is powerful machine learning system now still need a large cost. For example, in this simple example, Go game, it needs 50,000 times more energy and power than a human brain. And that means there are still a large gap between the energy cost of machine learning system and the power or energy capability of most of our daily life device. For example, smartphone, 1 watt would be a huge number. So the challenge is this 50,000 times gap is not decreasing. In fact, it's increasing. Here I summarize the complexity of machine learning algorithm in recent years in terms of the number of layers. We can see that as we develop the algorithm to solve bigger and more diverse problems, the complexity of the algorithm increases exponentially. So that's why, looking forward, I think for us as a community, one grand challenge is how we can develop machine learning that can do better than human, but also with much better energy efficiency. For example, going back to AlphaGo's example, we want them to do better than human, but with 50,000 times less better energy efficiency instead of 50,000 times more energy, right? So that's the research focus on my group. So we want to say how we can improve the energy efficiency of powerful machine learning system by orders of magnitude, but maintain the same performance. So the way I explained to my parents is how we can bring AlphaGo system to our pocket device. Yeah, thank you.
Good afternoon. My name is Anastasios Kyrilidis. You can call me Tassos, and I'm an assistant professor at the computer science department. So because probably I'm the least known person here, I would like to present myself. I'm Greek, even if I don't seem so. I actually got my undergraduate and master's in Greece, then PhD at EPFL. I want to mention that because that's my connection with the DSP. I'm actually the first PhD student of Vulkan. Then after that, I was a postdoc at UT Austin, and before joining RISE, I went to IBM as a postdoc. So my interest is lies on optimization for machine learning or signal processing. I mean, I don't know how we call these things these days. And I'm really interested in designing and analyzing algorithms. So I don't have the time to mention some of the topics that I'm interested in, but I really want to make a connection how my research so far is actually affected by tools that come from DSP and especially, for example, compressed sensing. For example, I have designed tools to analyze data using prior knowledge like graphs, sparsity, low rankedness, that they're actually related with some applications in neuroscience. And because I'm really interested in optimization, sparsity and low rankness and these low-dimensional models are actually really a key component of my research. For example, I worked on provable matrix factorization techniques, low-dimensional model selection through the work with Vulkan at EPFL, and these days, for example, how we can use sparsity beyond signal processing. For example, if we want to train a neural network efficiently, how we can combine ideas like sparsity and distributed computing so that we can have efficient implementations. And of course, I'm really interested in the theory part of optimization problems. For example, understanding geometries that happen in some non-convex geometries, for example, matrix completion, low-rank, weighted low-rank approximation, or even shallow neural networks. And because I want to be really a nice guy here, I want to finish here by saying that a very interesting application where I feel that signals are really interesting, that's of quantum computers. So in collaboration with IBM, I'm working on how we can actually do debugging and verification of quantum computers. So here, for example, ideas that originate from signal processing like matrix sensing and low-rank reconstruction can be used so that we can understand, even for a small number of qubits at the level of 16 to 20, how we can actually use computational models to reconstruct and understand how the quantum computers work. Thank you very much for your time.
You're at the top of the leaderboard.
All right. Many thanks for giving me the opportunity. It's an honor to talk to so many giants in the field. My name is Reinhard Heckel, and I'm working in the intersection of machine learning and signal processing. And I'm interested in very much the same problems than like Sidney is interested in and Rich is interested in. So in particular, I'm interested in how can we use machine learning in order to solve classical inverse problems such as denoising, inpainting, super resolution, compressed sensing, and so on. So no matter how, what method you use to solve any of those problems, you will use like some sort of signal model, and Justin was talking a lot about these signal models. So traditionally, people have been using handcrafted models, and that's essentially what Rich has been doing for many, many years. These days, all the state-of-the-art methods are based on image-generating neural networks, which is what Rich is doing right now, right? So when I came here, like Rich was always making this joke that he wants to be like Sidney, right? Like become more like Sidney. So the younger faculty maybe want to take something from Rich. So I was thinking, well, what could I do? I could take the young Rich and the old one and combine them, and that's actually what we have been working on. So we've been working on combining handcrafted image priors, so that are non-learned, and deep neural networks which are learned, right? To have like a nonlinear image model that is non-learned, so it's handcrafted, but it kind of takes a lot of inspiration from deep neural networks. And that's called the deep decoder. It's a handcrafted image-generating network, and it's underparameterized, untrained, so a lot of conceptual similarities to wavelets, but it yields a state-of-the-art performance for things like compression, image restoration, and so on. So here's one example. It works very well for MRI, so it actually works better than a one minimization on a real-world data set. And yeah, that's what I've been working on. Another thing that I've been working on is related to DNA data storage. So what we have been doing is we looked into this problem of storing information on DNA, right? The question is like, well, why would you do that? And like, who would be interested in paying for that? Because it's very, very expensive. And it turns out there are people willing to pay for it. And these guys are willing to pay for it. So that's a rock band. It's called Massive Attack. And they actually paid us to use our technology to store their music, because they think it's so important, so it should preserve for very long.
Our research is focusing developing technologies to help maybe the problem some of you might be suffering from, such as like mental health, stress, sleep, and cognitive performance.
All of the above.
Then how can we support people to enhance mental well-being, resilience under adverse event, and performance? These are the topics we are focusing on in my research group. So our research group, Computational Wellbeing Group, focus on developing technology for improving health and well-being, especially on these 3 domains. First one is we are very interested in measuring human outside the laboratory in our daily life setting. That's why we are interested in measuring people's physiology and behaviors with like mobile, wearable, those non-invasive sensors. And after that, after we get the data, we have been developing like algorithmic models to robustly understand what people are feeling, also what people are doing outside the lab. And the number 3 is we also design and develop some systems to help people to improve their health and well-being. And for this technology, we have several different very interdisciplinary skills for doing this kind of research. And so we do some sensing technology as well as data science, like signal processing and machine learning. And we also care about people's emotion and medicine, like health and well-being, as well as human-computer interaction. So in the next few years, our group is focusing on developing this kind of personalized feedback system, including like sensing, inference, and intervention. And using sensing module, we are collecting people's physiological signals, behavioral signals using wearable, mobile, or even non-contact sensing like cameras or radars. And using those signals, what we want to do is we want to predict how people will be doing. Also, what kind of things are related to your emotion, for example, like your mood or health. So we are interested in doing like causal analysis as well. And another thing is we also provide some intervention, some advice or feedback about how people can change or their behaviors, or how can people change, improve their health and well-being. But in our research, we have a lot of challenges, as you know. And for example, we have a lot of noise in our measurement. We have a lot of missing data because, of course, we are getting a lot of data from non-control environment. We also have individual differences in our measurement, also our outcome variables. And compared to speech and image research, our physiological signals and behavioral signals are very hard to collect. So we can't really scale it up to like thousands of millions people's data set. And also for intervention, our challenge is also in user engagement. So we want to develop some system to engage people for using that kind of system for a long time. So those are the research challenges, and we are solving those challenges. Thank you.
So hello everyone, I am Anshumali Srivastava. I joined Rice Computer Science Department in 2015. And what I work on is I think about what can we do just by accessing memory locations. So what I will be talking about is, we all know compressed sensing, and what if we take a signal and use compressed sensing to store, compress the information, but what if I use those compressed sensing bits as addresses, what happens? And basically, what we discover is locality preserving hashing, and hopefully I'll convince you that it's a cool technology. So we all know about 1-bit compressed sensing. You take random measurements, and then you quantize those measurements, and that basically you can recover the vector if it is sparse. So in some sense, this bit has stores partial information about what the point is. And what I want here is that it's another way of saying it is even if I perturb the data slightly, the bits don't change. So another way, if I have 2 vectors, x and y, and they have the same compressed sensing measurement, then they are likely to be similar. Now, if I take this and combine this with the fact that in computer science, algorithms 101, that fetching something from a memory location is a constant time operation, then essentially what we can do is efficient search. So I'll take your whole collection of data, create a hash table, and store every point at a location given by its set of compressed sensing measurements. And when I'm given a query and I want to know what elements are similar to this query, instead of looking at every other possible point as a candidate, I'll simply compute the compressed sensing measurement of that query and go to that location and fetch a point from there. Now, I have been thinking about this for a while, and what we have discovered is essentially that what you're doing is a provable adaptive sampling in constant amortized time. So I don't even have to know the query, but I can guarantee that I'm sampling something which is likely to be more similar to the query. And this sampling has a probability distribution, which is the weirdest distribution I've ever seen. And it's kind of unique. If you tried any other, you are order n. Otherwise, it's order 1.
Is it non-Gaussian?
It's totally non-Gaussian.
Oh, Don loves it.
Now, what can I do with this? What can I do with this technology? So I think about large neural networks. One option is do matrix multiplication, backpropagation, TensorFlow. But there's this new wisdom is that if I have a very large neural network, 100 million parameters, then I can train the network by just picking out relevant neurons, relevant as in having high activation on the input, and doing feed-forward and backpropagation. The problem is, without computing all the activation, I don't know which one is which. And this is where this is useful. I'll reorganize my neurons based on their compressed sensing measurements or hashing. So every neuron, I'll compute certain compressed sensing measurement, store it at a particular location. Now, given an input, I will do some memory lookups and get the sparsity pattern of the neural network, roughly in constant time. And I'll only feed forward and backpropagate. Essentially, I have reduced the computation time of training neural networks significantly, and I can parallelize the updates because things are random and sparse, so they are unlikely to overlap. What is the result? So we implemented this system in C++ on a CPU and compared with TensorFlow on a V100, which is the best GPU available right now, on a 120 million parameter neural network, so a giant neural network. And what we observe is that with using a simple CPU, I can beat neural networks on GPU roughly by 2.7 times. And the plot here on the x-axis is the time in log scale, and y-axis is the accuracy climb. So no matter what accuracy you care about, this is faster. This was within a week after we put it. It was picked up by several media outlets. And what I want to say is, this is yet another strike from compressed sensing, this time in the form of hashing. If you think you are born a little late because this is too cool, it's not, it's still compressed sensing. So not very different. All right.